Section 7.3 is our introduction to a function called logarithms. They are tied to exponential functions. In fact, you'll find out that they are inverses. So it makes sense to, after studying exponential equations, to go straight to logarithms. Now, you probably have not seen logarithms before, so it's going to be important that you pause this video whenever you need to so that you can understand what's going on. Feel free to go back and forth and all sorts of things until you understand logarithms. The reason that we have logarithms is okay, so let's say we have 2 to the second power. Everyone knows that's 4. Cool. 2 to the third power, well, that's 8, obviously. 2 times 2 is 4 times 2 is 8. But if we have 2 to what power equals 6, how are we going to figure that one out? It's definitely not a whole number because we've already jumped from 2 to 3 and totally past 6. It's going to be some sort of decimal, and we discovered logarithms to help us solve this equation right here. Now, this equation is written in what's called exponential form. That's what we've been talking about for the last couple class periods. That would be b to the x power equal to y. So since it's equal to y, it's an equation I can plug in my calculator where it's base b and it's raised to some power of x. See how these are similar? Well, now we have what the inverse of that is called a logarithmic form. It solves for that x. And it's written as and said as log base b of y is equal to x. This is how we would solve for x in this situation. There'd be no way for us to do it other than using a logarithm. Log base b of y equal to x. Yeah, I know it looks really funky. You'll get used to it. But it's very easy to write these back and forth because these are inverses. And if you remember, inverses mean that they undo each other. So if we were wanting to solve for x, we'd have to go this direction. The first thing that we're going to do with these logarithms is be able to rewrite them in logarithmic and in exponential form. Okay, it's a vital skill to be able to write them in both forms. Your first example of the day is log base 2 of 16 equal to 4. We want to rewrite this into exponential form. Now, there is a saying that I want you to write down on your paper. It's not very PC, but it's definitely going to help you remember. It is the phrase, always wear a bra to the log bar. Always wear a bra to the log bar. And this is why this is important, okay? If we rewrote the letters from up here using bra and bar, they would actually work, so we know where to put each letter. We have base b raised to the r power equal to a. See how it spells bra? It is rewritten as the log, that's supposed to be an L, log of the b of a equal to r. Bra, bar. Bra, bar. So if you see where those letters are supposed to be, it's very easy to rearrange it. Okay? Log, this is the log bar, so this is b, this is a, this is r, and if we wanted to rewrite that into exponential form, all we have to do is say, wear a bra to the log bar to ourselves. So we've already spelled bar, we need to spell bra. So this would be 2 to the 4th power equal to 16. Well, that makes sense, because 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 to the 4th is 16. Your calculator would prove that to you. Okay, I want you to take a couple minutes, pause the video, and try these next 2 examples to see if you understand how to rewrite it from logarithmic form to exponential form. Go ahead and pause the video and try now. When you say to yourself, always wear a bra to the log bar, we would rewrite these as this is B-A-R, so this is B-R-A. Makes sense. 12 to the 1st power is 12, that's true. And we try again. Log bar, so B-A-R. That's also true. Anything to a negative power is going to flip your fraction, which would give you 4 over 1 or 4. Okay, not only will you be asked to rewrite it from logarithmic form, you may be given it already in exponential form and asked to write it in logarithmic form. Okay, this time you're not given bar, you're given B, R, and A, bra. So you rewrite them into logarithmic form. This would be log base b of a equal to r. Bra, bar. Okay, so you're just rewriting them in different forms. These are inverse functions. They undo each other. Again, I want you to take a second to try to write these in logarithmic form, these next two examples. See if you can get it to writing it in logarithmic form from the exponential. Number 5, this is BRA, so we have log bar BRA, so we have log B A R. If you remember our exponent rules, these all make a lot of sense. Okay? It's a natural progression from our exponent rules to get to these. The second type of question you will be asked today is evaluating logarithmic functions. Sorry, logarithmic expressions. Examples type 2. So this time you're asked to evaluate. You have to think to yourself, what power of that will give me the answer? So the first one, we're asked to evaluate log base 4 of 64. You're like, well, I don't know. Okay, you have to ask yourself this question. What power of 4, since that's my base, it's my b, what power of 4 gives me 64? What power of 4 gives me 64? 4 to the first power is 4. 4 to the second power is 16. But if we raise 4 to the third power, and you know that as 64, that means that if we evaluate log base 4 of 64, we'd get that exponent of 3. What power of the base will get me this number? What power of the base will get me this number? Example 7 for today is the same type of question. We have log base 36 of 6. So I say to myself, okay, well, what power of 36 would get me 6? I'm trying to go the other way, so that means we're not taking a power with a whole number. We're going to use a fraction. If you remember that the square root of 36 is 6, another way that we could write square root is 36 to the 1/2 power. So since I know what exponent will get me back to 6, therefore log base 36 of 6 is equal to 1/2. If this is confusing for you, stop, go back to the beginning when I started explaining this example, and listen to it all again. If you're hanging on, I have 2 examples for you to try. This is log base 5 of 0.2 and log base 2 of 32. So now's your chance to decide if you're good enough to go on or you need to go back and watch a little bit. So take a moment, make a decision for yourself, and try these 2. Log base 5 of 0.2 can be rewritten as log base 5 of 1/5. Okay, this makes it easier for me to see because I know that raising any number to the negative exponent power will just flip that number to the denominator. Okay, right here I know what power of 5 will get me to 1/5. Well, obviously it's -1. That's what I know from my exponent rules. Therefore, evaluating log base 5 of 0.2 would have to be -1. This one, I want to know what power of 2 will get me to 32. So I test out my 2's. 2 to the first power, that's 2. 2 to the second power, that's 4. 2 to the third, 8. 2 to the fourth, 16. 2 to the fifth, 16 times 2 is 32. Bingo! So what power of 2 got me 32? I hope you say 5, because that's right. So we would say that the log base 2 of 32 is equal to 5. Now there are two types of logarithms. They're both very important and they're both awesome. The first type of logarithm is the one we're actually just using. It's what's called a common logarithm. Common logarithm. It's called common because its base is 10, just like our number system. Log base 10. So this typical common logarithm can be written as log with base 10, just as we've been writing it, or in shorthand, because mathematicians are lazy, if you see a log without a base, without anything written right here, it's an invisible 10. Okay, that's a common logarithm. Again, if you see just the word log written without any number as its base, it's a base 10. That's what you have to assume. The second type of logarithm is what's called a natural logarithm. This one is not base 10. It's natural, and if you remember that we learned about the natural base, that means that it has a base of the number e, which if you don't remember, that's approximately 2.17 something. Okay, repeating, or not repeating, irrational, you know what I mean. So this time, it could be written as log base e, or again with the shorthand, it's what's called natural log, and unfortunately we write it backwards. We write it ln. It's natural log, but you write it ln, natural log. The fun thing about these, though, these common and natural logarithms, since there are two most basic forms, is that our calculator can evaluate these for us. If they don't have that base, we have to do like we did on the other page and evaluate them ourselves. But common and natural logs can be evaluated with the calculator. Now, if you look at the calculator, there is a button, and it literally says log. Sorry, my calculator is all sorts of wonky. That button is over here next to your numbers. You have a button that is your log button. It assumes that you have a base of 10, and you have a natural log button. It assumes that you have a base of e. So our calculator will be able to evaluate these types of logs very easily for us. Our first example, that will literally just be pressing buttons in your calculator, is if you see log base 10 of 8. Now, the 10 is not written there, but because it's not written there, I assume that it's a 10. The great thing about this is that I just get to go press the log button, type in an 8, and press enter, and it will evaluate for me. So we know that this is approximately 0.903. Boom, we have evaluated this this common log using our calculator. Again, you can only use your calculator to do these if the base is 10 or invisible, or you're actually using a natural log. So in number 11, let's say we have natural log of 0.3. Well, again, we have a natural log button. This is ln right there. So we would just press ln of 0.3 and let the calculator do the work for me. Because there's no way I would know what power e needs to be raised to get me 0.3. Absolutely not. So we let the calculator do the work for me. This is negative 1.204. Again, these are the only two types that can go into the calculator. The next section is actually using these inverses, or inverse rules, to simplify logarithms. Using inverses to simplify logarithms. Okay. If you notice that you have a big base b that is then raised to the power of a log that has the same base. Okay, so this is a log with a base b, but it's actually the exponent to a giant B. Because these are the same base and base, it's like they cross out. They're gone. The only thing that's left then is the x from right here. See this guy? He does not get to cancel out. just the base b and this exponent cancel. This x gets to escape, and that is how we simplify. Okay, same makes sense if your base is e. So let's say that you have big base e raised to the natural log of x. What is the invisible base of a natural log? It's e. So now if my base and my little base match, they cancel out, and that x gets to escape. The other property with logs is the opposite way. So let's say we're not starting from an exponential where something's raised to a power, but we have log base b of b raised to the x power. Base and base. See how it's the same right here? And we still have a power of x? Essentially what happens is that this x still escapes, boom, gets to come over here, and these cancel out. So then again, whatever it's raised to that power gets to escape. So if you have a natural log of e raised to the x, what's the invisible base of a natural log? It's e. So if the little base and the big base match, e and e, they cancel out. And we'd get that this is equal to that exponent x. There's a lot of canceling that goes on, and it just takes a few examples to kind of understand what's going on. But this is a really important fact if you're planning to go on in math at all. If you get into pre-cal or calculus, you will be expected to know how to work with logs and reduce them pretty quickly. So take some time to learn this now. Let's see, for example, if we have 10 to the power of log of 4, well, there's no base here written at the log. So what's the invisible log base? You're right, it's 10. I hope you all said 10. So since the big base and the little base match, they cross out, and all that I'm left with is 4. Let's say we have 8 raised to the log base 8 of x. Okay, this is this rule right here. The base and the little number, so what's being raised to a power and the little number here, are the same. So they cross out. Don't want to use green. They cross out, and I'm left with just that other number, x. Let's say we have log base 7 of 7 to the negative 3x. If the base of the logarithm and the number here are both the same, like double b's here, double 7's here, these cross out, and I'm left with just negative 3x. See the patterns? You're looking for things to match. You want the big numbers and the little number here to match, or the little number and what's raised to the power to match. That way they cancel. Now in number 15 and 16, it's not going to be the case. We have log base 5 of 25 raised to the x power. I can't reduce these right now because this number here, the base, and my a value are not the same, like the 7's are the same here. So we have to kind of make it work. We can rewrite this though. Log base 5 times 5 squared to the x power. What's 5 squared? Don't say 10. It's 25. 5 times 5 is 25. So I haven't changed anything. I've just rewritten this equation. Using exponent rules, I know I can combine these by multiplying. So this would be log base 5 of 5 to the 2x. But since now that my little base and my a value match, they cancel, and I'm left with just 2x. I'm going to put one more on here. I want for you to try it, so pause this video and try it. All these problems are very quick, I know. Log base 2 of 64 to the x power. This is like number 15. Please give it a shot. If we were to rewrite this to the power of 2, 64, we found out earlier, is 2 to the 6th power. So I rewrote 64 with its base of 2. 2 to the 6th power is 64. Nothing changed here. I just got it to where my base and my a value are the same. I can combine my exponents here with multiplication. This is log base 2 of 2 to the 6x. Base and the a match, cross them out, and I'm left with 6x. How'd you do? There's 2 more sections. So one of the last sections for today is finding the inverse. Find the inverse. Number 17 here. We're given f of x is equal to 6x, and we want to know what the inverse of that function is. First thing we need to do is decide if it's in logarithmic or exponential form. Because you don't see the word log written anywhere, this is an exponential form. So that means we are going towards logarithmic form. Exponential, if you have exponential, it'll then take you to logarithmic. Those are the inverses. So we write this as y equals 6 to the x. Finding inverses, first step is replace the f of x with y. Second step is to switch the x's and y's. This should sound familiar. And now my job is to get it to say y equals. The only way I can get this number, this y, to be by itself is if I rewrote this into logarithmic form. Remember, this needs to be bra to log bar. So the b is 6 since it has an exponent, so this would be log base 6. The a is on the outside, equal to y. So my inverse, f inverse of x, is actually log base 6 of x. This is the inverse function to 6 to the x power. Okay, the steps for finding inverse were the same. The only difference is once we get here, the only way to get y by itself is to rewrite this in logarithmic form. That's the key. Okay, let's try number 18. This is f of x equal to natural log of x plus 3. I'll do this one with you. This one is given to us in log form. So that means we are going towards exponential form. We know that we should end up with something that has an exponent of x. Okay, first step in finding inverses is to replace f of x with y. Second step is to replace the x's and y's. Third step is to get your y by itself. Well, my y is currently stuck inside this natural log function, so I have to get rid of the natural log somehow. The inverse of a natural log is raising something to the e power. So let's go ahead and raise both sides to the e power. The reason we do this is because now e is raised to the ln of e. Remember that little base that's hidden right there? If the base and the a value match, base and base, these cross out, and I'm left with the exponent. So I'd have e to the x equal to y plus 3. We are one step away from having y by itself. It should be pretty easy. We just have to move this this 3. So since it's plus 3, we subtract 3 on both sides. We'd get y is equal to e to the x minus 3. Quick check, did I go from a logarithmic form to something with x as an exponent? I did, so that's a good sign. We have f to the negative 1 power of x is equal to e to the x minus 3. That is the inverse function of natural log of x plus 3. I guarantee that this part is probably a little muddy. Today is the first day that you learned about logs, and not only have we talked about them, but we've also used them to find inverses. Hang on, it's not that bad. We will keep practicing. You have a lot of practice problems. The only other thing that I need you to do today is you picked up a graph of logarithmic equations. So you do not lose this picture of the logarithmic functions, go grab a glue stick, cut it out, and glue it right here. Okay? It needs to be glued there so that we can look at it. Pause this video and go ahead and do that. When you have it glued down, and I would take this note page home with you for reference for when you're doing your work, because you're going to have to talk about the asymptotes of these functions. If you remember that an asymptote is a line it'll get close to and never cross. For our growth and decays, they were our x-axis. For logarithmic functions, they're this dotted line through the center, y equals x. I'm sorry, they're the dotted line here, x equals 0. The vertical asymptote. It's invisible dotted line, but it goes here. So this is the exponential group. This is what we already studied. This is exponential growth. So its inverse, which is reflected over the line y equals x, no longer has a vertical or horizontal asymptote here, but has a vertical asymptote along the y-axis. So it has on the y-axis, this is its vertical asymptote. If you had a decay function, see how b of x is coming down, so this is decay. Our inverse, or our log function for this decaying function, would be reflected over the line y equals x, and it would look something like this. Its asymptote would still be the y-axis, just like the exponential's asymptote is the x-axis. We look at the domain. It's easier to see here since the graphs aren't all clobbered over each other. The domain is always going to be greater than 0 because the range of g of x is greater than 0. So the domain and range, remember, if you restrict a domain in the original, you have to restrict the range in its inverse. Since these are inverses, their domain and range will always be the opposites. Okay. Spend some time looking at these graphs. Graph a few, make up some numbers for yourself. We will spend more time translating these functions. Again, there's such transformations that I told you needed to know. Next class. Okay. Do your best. You got this.